Okay, we have a couple more things to look at here in section 1.3. We're going to look at piecewise functions, or sometimes we just call them piece functions for short. And we're going to look at the difference quotient and how to evaluate that and simplify it. It's really just a lot of algebra involved there. Alright, so here's an example problem where we've got this cell phone company that's offering two different plans. Okay, one plan is $20 per month, okay, and that buys you 60 minutes. And then additional time is 40 cents per minute. Okay, so if you just going to use 60, you just $20 a month. But if there's anything over that, then you get charged extra per minute. So we're going to represent that mathematically by writing this cost function, where the cost is a function of the time, the number of minutes. And we really have two different things going on. The $20 per month buys 60 minutes. So anything up to 60 minutes is only going to cost us $20 per month. Okay? But if we should go over 60, where t is greater than 60, then we've got this additional charge of 40 cents per minute. And the t minus 60 is just going to represent how many minutes over the 60 we're going. Okay? And this is what we call a piecewise function, because it's not just one function over the entire domain, over the entire set of numbers, but we have different values depending on what part of the domain we're looking at, which x values, which inputs we're looking at, dictates which part of the function that we're going to use. Okay? So if we were to look at the graph of that cost function, where we have, up here we have c, the cost is the y-axis, and then time is the number of minutes is our x-axis. Notice that we were constant from 0 up until 60. Okay, we've got 60s right in here in between. And then once we hit that, then we have that 40 cents per minute, so we have our slope. We have our values are increasing again. Okay? So if we wanted to evaluate and interpret the following pieces for different time values. Okay? So if we were at c of 30, okay, well, 30 is between 0 and 60, okay, which means we're using the part of the function that was just equal to 20. So c of 30, the cost is going to be $20 because we haven't exceeded that 60-minute time limit. And if we were to go up to the graph, c of 30, somewhere right in here, we come up, see we're still hitting that horizontal, we're still hitting that constant value of 20. Okay. If we were to evaluate c of 100, then we have 100 is greater than 60, so we're using the second part of the function. We're using where the cost is 20 plus that 40 cents times whatever the difference is. So c of 100 is going to be 20 plus 40 cents times 100 minus 60. Okay? So we end up with c of 100, let's see, that'd be 40 times 0.4, so that'd be 16. So we're looking at 36. Okay. Remember, 100 would be out here, we'd be coming up, we'd be hitting the graph up in this general area somewhere. Okay. So here we'd have 136. 100 minutes going to cost us $36. It's over that 60 minutes at the flat rate of 20. Okay, so just looking at a piece function, the value that you're using for your input determines which piece of the function you're going to use to evaluate it. Okay. So let's look at a second piece function, and let's just look at what the graph would look like. So here we've got two things. We've got f of x equals x plus 2 when x is less than or equal to 1. Okay. So if x were 1, and I would plug x in there, then I would end up with 3. So I would be at 1, 3. Okay, so here's my point at 1, 3. And I'm taking all the x's that are less than or equal to 1. Okay, which means I'm going to jump back to 0. And then I'd have 0, 2. If I put in negative 1, I'd have negative 1, 1. Okay? So for the first piece of the function, we have this line coming back this direction. Okay? That represents this first piece of the function. The second piece of the function says whenever x is greater than 1, we're just going to graph 4. F of x is equal to 4. That's a constant. So up here at 1, I'm going to jump up to 4. I'm going to have an open dot because the 4 is not defined when x is 1. It's defined when x is greater than 1. And I'm going to have a horizontal line. Okay? So the first part of the function is looking at values for x that are less than or equal to 1, and they're defined by the function f of x equals x plus 2. When x's are greater than 1, then we're defined by the function f of x equals 4, the constant. So we have a piece function. We have different pieces of our graph. Okay? So we just kind of graph them individually, and then the whole thing together makes up our function f of x. Okay? One of the most common piece functions we see is called the greatest integer function. And it can be represented in two different ways with the notation. We can use this int with the x in parentheses, or we can use these kind of double-walled square brackets. That also represents the greatest integer of x. Okay? And the greatest integer function is also sometimes called the step function because when you graph it, it looks like stairs. Okay? So for all of the x's from 0 up to but not including 1, the y values are always 0. As soon as we get to 1, then we jump up. So if I look at the greatest integer of 1, when x is 1, I jump up here and I'm at y equals 1. Greatest integer of 1.3, okay, so now I'm here, I still go up, I still have a y value of 1. Or 1.5, I still jump up to that same y, that same function value at positive 1. Okay, so what do you think about the greatest integer of 2.4? Where would that be? 2.4 is going to be somewhere right in here. We'll change colors there. Okay. And notice when we go up and hit the function, we're at a y value of 2. So the greatest integer of 2.4 is 2. Okay. So if our input, our x is a 2.4, the greatest integer we're going to get out of that is 2. Okay. So that's a function that kind of shows up here and there throughout pre-calculus and calculus, but it's one that we want to be familiar with. All right, last thing is difference quotient. Okay, so before we talk about what the difference quotient looks like, I want you to see if you can write an expression to find the slope of that line. See if you remember what slope is from Algebra 1. Okay. Remember that slope is nothing more than the change in y compared to the change in the x's. Okay? So I'm looking at what we would call delta y and delta x. Delta is a symbol for change. Okay? So delta y over delta x would be our slope of this line L if we were just using straight x and y coordinates. Okay? At that more in terms of a function notation. So instead of x and y, I've got x and I've got some function f of x. Okay. So here's our function f. We've got our f of x axis, our function values, really just our y values, and we've got x. So let's say I have some value here. We'll call this x. And we're going to slide over here just a little ways, and we're going to look at another value. But we're not going to call it x, we're going to call it x plus h. I've moved over from x some amount, we don't know what it is, we've just moved to the right. Okay? So if we look at the ordered pairs, this ordered pair here would be the point x and f of x. Okay? What about the second one? What would we call that? Well, that ordered pair, the x value is x plus h, because we've now moved over. And the second part, the range value, would be f of x plus h. Okay. So what if I were to look at the line that's now going through those points? Okay. This line is what we call a secant. Okay. A secant line is one that's going to intersect the function at 2 points. Okay. So, and let's say I wanted to know the slope of the secant. How would we figure that out? Well, the slope of the secant would be just like finding the slope we did with x's and y's. we take the change in the y values, which in this case is f of x plus h minus f of x, divided by the change in the x values, x plus h minus x. And when we simplify there a little bit, we end up with f of x plus h minus f of x divided by, well, the x's are going to cancel out, and it's just going to be divided by h. Okay? And this here is what we call the difference quotient. Okay? And this is a very important relationship that allows you to move into calculus. Okay? When you start talking about limits and the limits of the difference quotient, that gets you into the tangents to the curves, and that gets you into derivatives, and that's kind of one of the main focuses of calculus. So even though we're just going to kind of touch upon this a little bit, this is something that comes up again later on, either at the end of this course or at the beginning of a calculus course. That is a very important concept. This difference quotient is a big deal when you start talking about getting into calculus. So we're just going to look at being able to evaluate that a little bit. Okay. So the difference quotient of the function 2x squared minus x plus 3. Okay. Well, remember that the difference quotient is f of x plus h minus f of x all divided by h. So we have to evaluate f of x plus h, which means I'm going to go back to this function, and wherever there's an x, I'm going to replace it with x plus h. So it becomes 2 times x plus h squared minus an x plus h plus 3. Okay? So all of that is just the f of x plus h. That's just this part. Now we have to subtract the f of x. Well, f of x is just the original function, 2x squared minus x plus 3. And the whole thing is divided by h. So at this point, this problem just becomes a whole bunch of algebra, a whole bunch of simplifying. Okay? We need to take this numerator, simplify all that down, and what we'll find is that if we do everything correctly, we'll have a lot of pieces just start falling out. Okay? So first thing is we've got to square the x plus h. So that's x squared plus 2xh plus h squared. That's our binomial squared pattern. Then I'm going to distribute the negative, minus x minus h plus 3. Now I'm going to have to come over here and distribute this negative through all three of those terms. So minus 2x squared plus x and minus 3. Okay? And all of that is still divided by h. So we can already see right now we got some things to get rid of. Minus x plus x, those are going to go. Plus 3 minus 3, those are going to go. Okay? If we look at distributing out here with this 2, we've got a 2x squared plus 4xh plus 2h squared. Okay? So what else is going to happen? Well, here's the minus 2x squared and the plus 2x squared. Those are going to go. So what are we left with? We're left with 4xh plus 2h squared minus h all divided by h. Okay? So what do all those things in the numerator have in common? Well, they all have an h. So if I factor out the h, I'll have 4x plus 2h minus 1 divided by h. And now once again we can divide out, simplify those h's, and we're down to 4x plus 2h minus 1. Okay? That is our difference quotient. Okay? Now, it looks kind of strange. It doesn't really look like it would do us any good at all, and right now, really, it doesn't. Okay? This is just kind of a preliminary building block for looking at limits and looking at derivatives further down the road. Okay? So this is something that we will revisit later, hopefully, towards the end of the year, and if you go on and take calculus, you definitely will revisit it at the beginning of a calculus course. But what this has to do with is our ultimate goal is going to be that the h will get smaller and smaller and smaller until eventually it's gone, and this will allow us to find the slope of a curve at any given point, and that's really what doing derivatives in calculus is all about. Okay, is finding the slope, finding the instantaneous rate of change, how things are changing right now rather than over a whole entire interval. Okay, so take a minute, try this problem in your notes, maybe pause the video, see if you can work this out, and then go back and watch the solution and see how well you did and make sure that you've got it all right. Okay, so f of x plus h would be negative 2 times x plus h squared plus x plus h plus 5. So all of that, okay, all of that is the f of x plus h. Minus, I have to subtract the f of x, or the g of x in this case. Negative 2x squared plus x plus 5. And the whole thing divided by h. Okay? So again, once we've got it set up, it's just simply a matter of simplifying. It's just a lot of algebra work. So we've got negative 2. When I square, I'm going to get x squared plus 2xh plus h squared plus x plus h plus 5. Now distribute my negative. I've got a plus 2x squared, a minus x, and a minus 5, and everything is still divided by h. Well, plus x, minus x, they're gone. Minus 5, plus 5, they're gone. When we distribute over here, we'll have negative 2x squared minus 4xh minus 2h squared. So what's going to happen? Negative 2x squared, positive 2x squared, they're done. So I have negative 4xh minus 2h squared plus an h, all divided by h. So again, I look at the numerator, I can factor in h from all of those terms in the numerator, and then when I divide by h, my h's will divide out. And I will be left with negative 4x minus 2h plus 1 as my difference quotient. Okay. Alright, so hopefully that makes a little bit of sense, and we will we'll look at doing some more of these problems in class tomorrow. Like I said, the difference quotient isn't really a difficult thing right now. It's just kind of the introductory. It's getting used to doing all of that algebra and all of that simplifying, combining like terms, just to try to kind of simplify it down to a smaller expression, which later on we'll take one step further. Okay? All right. Thank you. We'll see you tomorrow.